Hi everyone, this is Zixuan from Hong Kong U, and this is a presentation for the optimal for approximation for the correlated Pandora's problem. This is a joint work with Nikhil Bansal from U Michigan and Huang from Hong Kong U. Pandora's problem was originally proposed by Weizmann in 1979, and there are n independent Pandora's boxes, each associated with a volume and an opening cost. The exact value of the opening cost and the distribution of the volumes are given ahead. Please note that in very classic version, the distributions of the volumes are independent. And in each round, they have two choices. You may either pay the cost to open the box and see its true volume. Here, suppose we first open the second box and see the true volume is 5. Then we pay C3 and see the true volume of the third box is 3. And we pay C4 to see the fourth box has volume 4. And you may also decide to take an open box and stop the procedure. Here, suppose we take the third box whose volume is 3. The goal of this process is just to minimize the total cost spent on opening boxes plus the volume of the box that we take in the end. And in this example, we have the total opening cost C2 plus C3 plus C4, and then plus the taken volume, which is V3 equals to 3. So the total cost is 6.5. And this problem indeed characterizes lots of real-life scenarios. For example, if you want to buy something and only know its rough price in each market, you need to pay some efforts to visit the shops in order to see the true prices. And definitely you want to buy at the lowest price, but you cannot visit all the shops due to some time or traffic costs. So the key challenge of this task is to trade off between the exploration cost and the exploitation cost. And this problem itself has a very simple and elegant solution called Weizmann's rule, and it uses some amortization techniques and try to charge the opening cost of the boxes into the volumes inside, so that we can simply assume that the boxes are free and we can apply some simple greedy algorithms. In this work, we studied the correlated version where the volumes of the boxes can be correlated. And this correlated version was first proposed by Chola et al. In 2020. And here we call a certain realization of the volumes as a scenario. Once you open a box and see its true volume, due to the correlations between the boxes, some scenarios will be naturally unavailable. So in this example, suppose you open the second box and see the volume is V2 equals to 4. So the only remaining scenarios will be the scenario that V2 equals to 4. And in this setting, you may open a box not only for its own volume, but also for the information of some other correlated boxes, so it's much more tricky. This correlated version is closely related to a very classic problem called min-sum set cover, which was proposed by Fighi, Lawaz, and Zitelli in 2004. In min-sum set cover, you are given a ground set of elements and a branch of subsets, and the subsets can be overlapping. The goal of this problem is to find an order of the subsets so that average cover time of all the elements is minimized. And here we define the cover time of a certain element to be the first time that it is covered by the subset in this order. In this example, suppose we order the subsets in this way, and the first subset covers A, B, G, so the cover time of them is 1, and the second subset covers F, D, H, the cover time will be 2. The third subset covers 2 new elements, C and E, so the cover time of them is 3. The fourth subset covers nothing new. And the average cover time in this example is 15/8. Indeed, greedy algorithm gives an optimal solution of this problem, which is a full approximation. Here, greedy simply means that in each round, you try to choose the subset that can cover the maximal number of new elements. Indeed, min-sum set cover is a special case of the correlated Pandora's problem, where the volumes are either 0 or infinity. So, with all of generality, we assume that all the scenarios happens with the same probability. We can consider the boxes as the subsets and consider scenarios as elements to be covered. So suppose V1 corresponds to subset 1, V2 corresponds to subset 2, and V3 subset 3, V4 subset 4. So in each scenario, it is covered by the first zero volume box because we will never take a box that has infinite volume. So you may see that scenario A, B, G are covered by box 1, and scenario D, F, H are covered by box 2, and C, E are covered by box 3, and indeed the fourth box covers no new scenarios. So because the taken volume is always 0 and we assume the opening costs are 1, so the only cost of the algorithm comes from the box opening cost, which corresponds exact to the average cover time in the min-sum set cover problem. And by this reduction, we have a natural lower bound of 4 for the correlated Pandora's problem. The first approximation result for the correlated version was given by Chola et al. In 2020. They first formulated a linear program and reduced the problem to min-sum set cover to find a proper order of opening boxes. And then they provided a generalized ski rental algorithm to find the stopping time. And this overall gives a 9.22 approximation. And Jagatsali and Zamos later improved the ratios into 4.428 by generalizing Weismann's rule and using an analysis quite similar to min-sum set cover. And in this work, we gave an optimal 4 approximation through LP rounding and a stopping algorithm that we called balance stopping. Our first step is to interpret both the box opening cost and the taken volume as the time cost for easier formulation of the later linear program. Suppose this is the time horizon. Assume we first spend time C2, C3, C4 to open boxes 2, 3, 4 respectively. And then we decide to take box 3, so we spend an extra time of V3. In addition, we try to define the status of a box in the following way. So let's consider the third box. It is originally closed, and at time 1, we start to open it, and the opening cost of box 3 is 2. So we say that box 3 is being opened during time 1 to 3. And afterwards, we say box 3 is opened. And in the algorithm, a box is available for being taken as long as it is opened. Let's see the linear program relaxation. And we first assume that the opening costs are 1 and the volumes are integers for simplicity. And we refer interested audience to our full paper for the details of general case. We define 2 branches of variables. The first is xit, which denotes the probability that box I is being opened at time t. And under this unit cost assumption, this means that we use the tth time step to open box I. And variable zit conditional on v denotes the probability that box I is being opened at time t and is taken in the scenario v. Because in this formulation, we suppose that the algorithm can always stop optimally. So if box I is being opened at time t and it is taken in scenario v, the total opening cost is simply t and the taken volume is vi. And this formulates the objective. And the first constraint says that we can open at most 1 box at a time. And the second constraint means that exactly 1 box is taken in each scenario. The last constraint says that we can only take an open box. This formulation is essentially the same as the one used by Chola et al. In 2020. For the rounding procedure, we'll apply a Poisson rounding. We denote bar xit to be the average of the xit prime from time 0 to t, and recall that xit is the probability that box I is being opened at time t, so this bar xit can be considered as the average probability that box I is being opened during time 0 to t. And this definition is inspired by the work of Bansal et al. In 2021, which gives a new optimal solution to the min-sum set cover problem through LP rounding. A very crucial property here is that the sum of bar xit over all the boxes is at most 1, as we can open at most 1 box at a time. And consider a Poisson process such that each box I arrives with arrival rate bar xi t over 2. The arrivals in the Poisson process naturally map to an order of opening boxes. Let's see this illustration. Suppose this is the Poisson time, and box 1 arrives here, box 2 arrives twice, and box 3 arrives here. So in the real time, we first open box 2, then box 1, then box 2. We even allow this redundant cost in the analysis, and then box 3. And by the crucial property, the total arrival rate at each time is at most 1. So in the end, we have that the real time is at most the Poisson time in expectation. This Poisson rounding procedure indeed gives a very efficient order of opening boxes. We will show that if we can always stop at the best box, then we will get a full approximation. We will show the full approximation for every scenario V. The expected cost of our algorithm in scenario V can be written into the sum over threshold theta, the probability that LG is at least theta conditional on V. And recall that the cost of the linear program in scenario V is the sum over time t over boxes I, the t plus vi times zit. And this benchmark is only related to z variables without the x variables. And in addition, it is linear in z. So our goal is try to relax the expected cost of the algorithm to get a linear form in z. Firstly, for any threshold theta, the probability that the algorithm's cost is at least theta is exactly the probability that each box I has no arrival in the Poisson process until time t, such that t plus vi is at least theta. And this probability can be written into a product over boxes I, thanks to the independency of the Poisson process. And then for each box, the probability of having no arrival is simply the exponential of negative total arrival rates by the definition of Poisson process. And we may further expand the terms in the exponential by the definition of bar xi. And recall that we want to make it only related to z, so the first step is relax the x variables into z by the LP constraint. And then we want to linearize the expression, where we can apply Jensen's inequality thanks to the fact that the sum of z variables is 1. And the last step is to sum over the threshold theta to get the expected total cost, which finally is bounded by the sum over t and I for t plus vi times z. And let's compare with the LP cost. We have a factor 4 before time t, so we get a full approximation. A key observation here is that though the factor 4 is tight for the time term t, we still have some slackness in the factor of volume vi. This motivates us to find some stopping rules such that we will only lose some extra factors for the volume term. Our attempt here is called balance stopping, which gives the correct solution. In this scheme, we activate each box I at time t equals to vi. And suppose this is the Poisson time. Box 2 arrives here, and on arrival we see its volume v2, so we activate it at time t equals to v2. And same for box 1, we activate at t equals to v1. And when box 3 arrives, we see v3 and activate it at t equals to v3. And then we take the first arrived and activated box. In this example, we will take box 3 because on its arrival, the realized volume is smaller than the arrival time, so it is naturally activated, while box 1 and 2 are not activated yet. And in this balance stopping, we make sure that the taken volume is at most the real time that we spent on opening boxes, which means that the volume is small enough for being taken. And this somehow balances the exploitation cost and the exploration cost, so we call it balance stopping. Since the whole proof is quite technically involved, here I will skip the details but give some very high-level ideas of why this balance stopping works. Recall that this is our arrival rate at time t. We can decompose it into two parts. The first part is only related to z variables, and this is well defined because z variables are less than or equal to x variables. And we call the variables triggers by z as good variables because z is related to the LP benchmark, and we can directly analyze and compare the variables with LP. And if we are lucky enough and only have good arrivals in the Poisson rounding, it will be not hard to prove the full approximation in the end. However, we still have the second part, which is the difference between x and z, and we call the arrivals triggered by x minus z as bad arrivals because they don't contribute to the LP benchmark, and we don't know how to charge and compare them with the LP. Indeed, in the Poisson process, we don't have the power to tell which arrivals are good and which arrivals are bad. So we have to make sure that even if we select some boxes from bad arrival, the total cost of our algorithm will not increase. So suppose this is the timeline, and here is a good arrival of box 2 at time t2, and the bad arrival of box 1 that occurs at some time t1 that is smaller than t2. And for any time t between these two arrivals, the good arrival rate is at most 2 over t by the definition. And further by the definition of the Poisson process, the expected waiting time from t1 to the next good arrival is at least t1. So if the volume of box I is at most t1, it's not worth it to wait, even if the coming box 2 has 0 volume, because the waiting time is already more than t1 in expectation. So this somehow shows the efficiency of our balance stopping. In summary, we first apply the LP relaxation and Poisson rounding to get a good order of opening boxes, and then we applied a stopping rule called balance stopping, and combining them together gives an optimal full approximation for the correlated Pandora's box problem. And that's all of my presentation. Thanks for listening.